In the last podcast, we were showing you where the electrons are placed or where they fill around the nucleus by filling these orbitals. They always start closest to the nucleus in the lowest energy levels, the first energy level, and then they build their way out. Within the energy levels, there are these sub-levels, the S, the P's, the D's, and the F's, that the electrons are placed into. As it turns out, the first energy level only has one sublevel, the s orbital. The second energy level has two sublevels, the s's and the p's. The third energy level has three sublevels, the s, the p's, and the d's. The fourth energy level has four sublevels, s, p, d, and f. And then from there on out, though the fifth energy level does have five sublevels, the sixth energy level does have six sublevels, we actually only use four of them. The reason why is by the time you would actually use those other orbitals, which are actually called G and H orbitals and so on and so forth, you actually run out of electrons. We don't have enough electrons that actually would be filled into those orbitals. Where we left off was with neon. Neon had 10 electrons. It completely filled the first energy level, the 1s. It completely filled the second energy level, which was the 2s and the 2p's, and it had an electron configuration of a 1s2, 2s2, 2p6. We are now to sodium, which is element 11, and because it has filled the second energy level, we have to move on to the third. So, if you notice, you have your 1s, this is your 2s, these are your 2p's, this is your 3s, this is your 3p's, this is your 4s, these are your 3Ds. For those who are pre-AP students, I can explain to you individually why the 4S comes before the 3D. You would think that the entire third energy level would be lower in energy than the entire fourth energy level, but as you start getting further from the nucleus, some different things start happening and the orbitals actually start overlapping in energy anyway. So you'll have to ask me that individually. But anyway, we're on to sodium with 11 electrons. So let's go ahead and place them in these orbitals. You have 1, 2, 3, 4, 5, 6, 7 individually, 8, 9, 10, and now we have to move on to the third energy level, and there's the 11th electron. And now you have a 1s2, 2s2, 2p6, 3s1. Alright, so this would be the electron configuration for sodium. Now, this is what's called the complete electron configuration. However, there is a way to shorthand this. The way to shorthand this is to use what is called noble gas configuration. And noble gas configuration is used because only the only the electrons in the outermost energy level are actually used in chemical reactions. Electrons that are in inner energy levels are shielded, and so they're not actually used. And so what you can do is you can say, well, if you notice 1s2, 2s2, 2p6 is the exact same thing as neon. What we can abbreviate this is say that sodium has a neon core. The inner electrons look just like neons, and then the outer electrons, which are called core or the outer electrons are called valence electrons. That should not be an S. Would be reported as 3s1. So the noble gas configuration for sodium is a neon core 3s1. It's a shorter way of writing the configuration. These electrons, again, are called core electrons. Some people call them kernel electrons. And then the outer electrons are called valence electrons. And it's only the valence electrons, these outer electrons, that are used in chemical reactions. Alright, so let's go ahead and move on to the next one. Whoops. Scrolling down here. Not scrolling, there we go. Okay, argon. We're going to move all the way across the periodic table to argon. Okay, argon has 18 electrons. So argon is going to be, and again, this is the 1s, 2s, 2p, 3s, 3p, and so on and so forth. Argon has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 electrons. It completes the third energy level, and its electron configuration would be a 1s2, 2s2, 2p6, 3s2, 3p6. That is the electron configuration for argon. When you move down to potassium, potassium is element number 19. Since the third energy level is filled, now you might say, well, wait a minute, what about the 3Ds? We haven't gotten to the 3Ds yet. Yeah, I know, the 3Ds actually get filled after the 4s. Here's the 4s. I'm going to show you on the periodic table how you can predict this. You won't actually have to memorize this. But when you get to potassium, with the 19 electrons, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and the last electron is going to go in the 4s. So its configuration would be a 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That's where those 19 electrons are arranged. Or if you wanted to use a noble gas configuration, you could collapse all of that down, because that's exactly like argon. Those are the core or kernel electrons. There's 18 of those. That looks just like argon. And then the valence electrons are 4s1. That would be the noble gas configuration for potassium, an argon core with 4s1 valence configuration. Now scandium, we're going to move over two atoms now to element number 21. Scandium has 21 electrons, and you're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and now you start filling that d orbital in the electron configuration. I'm going to shorthand this now. It has an argon core. The first 18 electrons look just like argon. 1s2, 2s2, 2p6, 3s2, 3p6, and now 4s2, 3d1 configuration. Alright? Now, you're really only required to know the first 20 elements up to calcium, and so you're going to want to practice those. We'll be talking about those in class as well. But for those who are my pre-APers, you're going to need to know the configurations of all the elements. But there's a way that you can predict these. Okay. And so in the next podcast, I'm going to show you how the periodic table actually tells you what the electron configurations are. You do not have to memorize all of the diagrams and diagram them out every single time. As you look at the periodic table, it will tell you exactly what the configuration is, and that's what we're going to do in the next podcast.